You need to put the infinity form, the infinity spells thing on the whole thing.
This is plus that, this minus sex minus that.
The exponent goes to 0, so then a to the 0 is 1. Yeah. How when you're doing something else, because it's just x is greater than delta. When you stick your infinity to when it goes to 8 to 9, is that not 0? Is that not 10? Yeah.
Because you also have this here. So go to infinity. So you have a number that go to infinity, another line goes to 0. Which one you need to determine which one is faster?
It's
exponential goes to faster, so that's why you become the number.
Right, okay.
What's the darkest one? Epsilon. So that's pretty much huge. Delta is
When you go to the yeah, but that's minus. It's minus 4 times.
Yeah.
So is this the expectation? Because what is this not? Is it
Okay, maybe I will just give you some key idea about how to tackle this kind of question. Now, first of all, you need to understand the meaning of biased and unbiased. An estimator is said to be unbiased for a parameter theta. We use this theta hat to estimate theta. So under what scenario this theta hat is said to be unbiased? It is when the expectation of the theta hat is equal to theta. We say that this estimator is unbiased. Otherwise, it is biased. So if you are asked to determine whether an estimator is biased or unbiased, we always start with finding its expectation. So in this question, we want to show that it is a biased estimator. So we find the expectation of the sample mean. And to find the expectation of the sample mean, you can utilize a property that was taught actually at the beginning of the course. The expectation of the sample mean is equal to the population mean. That is the property of the random sample. So what we need to do is to find the population mean in terms of the unknown parameter delta. And it is just simply an integral. Multiplying x to the probability density function, integrating over the whole range of the data. And in this probability function, it is e to power minus x minus delta. But to set the integral range, we need to base on the domain of the distribution, which is starting from delta all the way up to infinity. So as long as you can write down this integral correctly, then the rest will become a mathematics problem. We just simply make use of your understanding or basic knowledge how to determine this integral. And it will rely on a technique called the integration by parts. And I assume that all of you know how to do the integration by parts. And if you are not very familiar with this technique, maybe you can just try to understand and follow. So we just put this exponential function into the differential. And because we have negative sign here, so we need to attach a negative sign outside the integral. And according to the integration by parts formula, we can separate it into two terms. S multiplied to this quantity within the differential. Of course, evaluated over this range. And then minus. So that will become a plus because we have negative sign. The expression within the differential multiplied to d of s. integrating over delta to infinity. So this is the integration by part technique. So we evaluate this expression. We substitute infinity into s. When you substitute infinity into s, this exponential function will converge to 0. This s will diverge to infinity. But the exponential function will converge to 0 faster than s goes to infinity, so that eventually this will become 0. So when we put infinity into s, it will become 0. And if you put delta into s, this exponential function will become 1, and this becomes delta. So it becomes minus delta for the first term. And for the second term, it will be also an integral of the exponential function. So eventually, you will find that the expectation of the sample mean will be equal to the population mean, and the population mean is equal to delta plus 1. And it is not equal to delta. And therefore, Sn bar is biased for delta. It is not an unbiased estimator. So this is a general step and typical step how we prove an estimator is biased or unbiased. Okay? Any question? Now about bias, you always look into the expectation. And we can also determine a term called the bias. The bias of an estimator is equal to the difference between its expectation and the unknown parameter we want to estimate. So if the bias is equal to 0, then that means these two are the same, so it will become unbiased. But in this question, we find that the bias is equal to 1. And it is equal to 1 and remain constant even if you have a large sample, because it does not depend on n. Because the question asks us how this bias will behave if n tends to infinity. And actually when n tends to infinity, the bias will remain equal to 1. So in other words, no matter how large a sample you draw, if you use the sample mean to estimate delta, you are not actually targeting delta to do the estimation. You are always estimating something else. Okay? But this will also suggest a way for us to modify the estimator into an unbiased estimator. Because we know that expectation of S bar is equal to delta plus 1. And for an unbiased estimator, what we need to do is to find an estimator such that expectation is equal to delta. And this will suggest a very simple way for us to modify S bar. We may just simply subtract both sides from subtract 1 from both sides. And we will find that the sample mean minus 1 will be an unbiased estimator of the delta. So if you use the sample mean minus 1, then this will become an unbiased estimator for the unknown parameter delta. So this is also a reason why we study the bias of an estimator, because after we obtain the bias, it will suggest a way for us to modify it so that we can come up with an unbiased estimation. Is there any question? So now, let's move on to question number 5, which is a typical question on finding the so-called maximum likelihood estimator. So you may refer to the notes on maximum likelihood estimation on how we can write down the likelihood and not likelihood function and maximize it to find the MLE. And for your ease reference, I've already provided you the probability function of the geometric distribution here.
Do we need to get X and X to change it?
Separate them.
Yeah. Oh, okay.
And is this
Oh,
the sum of
minus
I
here.
equals 1 to n
Is
times 1
this
to n?
this one?
That's n over 1 minus b.
P is the weighted impact. The probability is so it's just a very long
We do different long videos and online. So it's just
And that's still over 1 minus P. Yeah.
sure that it's negative.
It's just it's low. So
Oh, shit, yeah. I guess why
I was doing so then I'll come back down. Yeah, but then I get two zero. Is that?
Okay, so this is also a typical question that you are asked to find an MLE. And you can always start with this step. The first step, write down the likelihood function. Now, likelihood function usually denoted by capital L. It is equal to the product of the probability function. So if you are given a continuous distribution, then this will be the probability density. If it is a discrete distribution, then this will be the probability mass function. So in this geometric distribution, the probability function is given by this, so that we multiply this all together for each sample point, xi, and we simplify it, we can get this likelihood function. I can see most of you can get this correct. And then usually we will work with the log scale. So we take the logarithm of the likelihood function to obtain the log likelihood function, usually denoted by small letter l. It is the logarithm of this expression. So this is the starting point if you want to find the MLE. The MLE is defined as the parameter value that maximizes the log likelihood function. So to find the maximum, we can use calculus. We differentiate the log likelihood function with respect to the parameter and set a equal to 0. And we solve this equation, we can get the MLE. So we differentiate this expression So this is just a constant multiplier. When we differentiate the logarithm, it will become the reciprocal. The derivative of logarithm is reciprocal. Now notice that this logarithm is the natural log. Okay, we are always using the natural log here for the log-like function. So the derivative of the natural log is equal to the reciprocal, but we have a minus p here. So according to the chain rule, we need to attach a minus sign. And similarly, n log p, the derivative is equal to n divided by p. And we set this equal to 0 to find the p hat. And this will give us an equation. So what we need to do is to solve the equation. So the n multiplied to p hat will be cancelled on both sides. So eventually you will find that p hat will be obtained as n divided by the sum of the x. And you can also express this in terms of the sample mean. So for the geometric distribution, the maximum likelihood estimator for the unknown probability p is the reciprocal of the sample mean. So this is a technique how in general we will be able to find an expression for us to do the estimations. Okay? But this is not the end, because you also need to verify that this is the point at which the log-like function attains its maximum. So we need to do the second derivative test. We need to differentiate the second derivative to obtain the second derivative, to see whether it is negative. Because according to the principle of optimization using calculus, at the maximum point, the second derivative should be negative. So we need to verify that this second derivative is negative. So we differentiate the first derivative, which is this part. We differentiate this one more time. Now, this is the second derivative, and we need to check that whether it is negative. Now, a lot of the quantity here, because both terms have a negative sign, and a lot of these quantities are positive, like n must be log negative, the square must be log negative. So the problem is only, the question is only on this numerator, sum of x minus n, whether it is positive or negative. And it always, usually, will be based on the domain of the distribution. From the distribution, there will always a range of the values for the possible value of the data. And for the geometric distribution, it starts from 1. So that means every of these x must be starting from 1, must be greater than or equal to 1. So we know that for the geometric distribution, xi must be greater than 1 for all the I. All of them are greater than or equal to 1. This is where we know that the sum of them must be greater than n. Because every of this number is starting from 1, so the sum of them must be greater than or equal to the sum of 1, which is n. This is where we know that this numerator is log negative. And therefore, this will be negative. Okay? Now, this is a crucial part if you want to verify that the solution of this equation is the maximum point. You need to check the second derivative. And when you check the second derivative, you will have an expression. And this expression, whether it's positive or negative, it will depend on a lot of comparison. And usually this comparison sometimes will be based on the possible range of the parameter and also the possible range of the data. Okay? For different model, for different other distribution, you will have a different way to determine the sign of the quantity in the second derivative. Okay? And you need to focus on, you need to take into consideration of the range of x. Okay? Any question? Now, we still have a little time, so maybe you can start working on question number 7, which is a typical question on numerical calculation of the so-called confidence interval. And for your ease reference, I've copied some formula from the lecture notes here. For the confidence interval of the population mean when the sample was drawn from the normal distribution. Yes. And.
basically.
Okay, so wait, then the other just have to but then
Okay, I have a few minutes left. It seems that you are not that familiar with this topic, so maybe I say a few words. Now, this is a topic about the so-called confidence interval. That means instead of using a single number to do the estimation, we provide a range of values. Now, first of all, it is based on the fact that if you have a random sample drawn from the normal distribution with an unknown population mean, but known variance, then the formula for finding the confidence interval is given here. In this formula, there are four quantities we need to determine: the sample mean, the population standard deviation, which is assumed to be known, the sample size, and the normal quantile. This is the normal quantile, 1 minus alpha of the 2 quantile of the standard normal, which is obtained from either from the standard normal distribution table or by using R. Just what you have done in the lab before. Now, in this question, we already have the sample mean here, which is equal to 100.8. And we are also given the standard deviation, which is 3.4. And the sample size is also given. So we have most of the ingredient for this calculation. The only thing we need to determine is this quantile. Now we have a value of alpha here. What does it mean by this alpha? It depends on the coverage. Because for each confidence interval, there is a number attached to it representing how wide this interval will cover. So if you want a 95% coverage, then the value of alpha will be equal to 0.05. So that the quantile in the formula will be Z.975, which can be obtained from the standard normal distribution table, or by using R, you will find that it is 1.96. And it is actually a regular number we always use, because it is corresponding to the normal quantile when we want a 95% coverage. And the 95% coverage is a commonly used quantity. So we have everything. So we substitute into the formula. The confidence interval will be obtained as 100.8 plus minus 1.96 multiplied to 3.4 over square root of 9. So this is just a typical question that you just find out all the quantity for the formula and substitute in the formula. And the quantity add to or subtract from the mean is called a margin of error. You can regard this as a possible size of error if we use the sample mean to estimate the population mean. And you can also use this to produce a range of value, subtracting the margin of error 2.22 from 100.8. And also add this 2.22 to the sample mean. This will be a range of the value. And we use this range of the value to estimate the unknown population mean. We call this the confidence interval. But you want to express how high the confidence is. And that is corresponding to the coverage, 95%. Okay? And if you want to have a higher confidence, you want to have a larger coverage, like in the second part, for 98%, then you need to change the value of alpha to 0.02, so that the quantile will become larger. From the table or from the R, you will find that it is equal to 2.326. then you change the value of this into 2.326, you will get the corresponding confidence interval for a larger coverage. Okay? You want to have a higher confidence, of course you need to have a wider interval. Okay? Is there any question? Now, one remark is that this formula is used under the scenario that when the population variance is low. In practical situation, usually this will rarely be the case. Sometimes the population variance is not long, and we need to estimate by using the sample variance. Then there will be another formula for you to use under that scenario. And that is what you learn in the coming lectures. So that's it. Sorry for overrun. Now there will be no class on the in the next few weeks, so we'll meet after the Easter break and enjoy your holiday.
Yeah.